What's going on, everyone? So this is take 2 of the week 5 video notes. So chapter 5 is getting into the physical database design and performance, and the introduction of this chapter talks about the purpose and the goal of the physical database design. So please review that, and then we'll get into the physical database design process. Now, of course, with every other chapter, we have our objectives. So please read those objectives and become familiar with those as you read the chapter. And again, like every other chapter, the chapter is certainly going to focus on those objectives and then add in quite a bit of additional information. But make sure that you have a good grasp of the objectives. So this chapter starts to get into a little bit about the data volume and usage analysis, and it just really scratches the surface on all this. So if you look at figure 5-1, which is actually it takes figure 3-5b from chapter 3 and kind of adds on to that, and it kind of talks about the amount of data that's being stored, as well as the transaction that takes place on these entities. So let's take a look at that. So the number in the lower right hand corner indicates the number of records in each entity, and notice that the part entity has 3,000 entities, and of those 40% belongs to the manufactured part entity and or subtype rather, and 70% belongs to the purchased part. And then there are 150 suppliers that provide 6,000 supplies to create those parts. And now this shows the access frequencies per hour, and there are 20,000 accesses in the part entity, and you'll notice that of the 20,000, 14,000 of those are directly from the database system, and then 6,000 are from some external source. Now you might recall from a couple of video notes ago that I indicated that some of the tables or relations that we use in our system may already exist and might already be used by other database systems, and likewise the tables and the entities that we have in our system are going to be accessed by other systems. Now typically when something like that happens, there is a pretty substantial amount of control over which systems can change the data, because of course if you have one system that is designed to manage and control the data in those tables, you don't want another system to come in and manipulate that data, and then the owning system kind of freaks out and breaks and doesn't know what's happening to its own data. But so there are 7,500 transactions coming into the supplier system, and then this shows the interactions between supplier and supplies, and the interaction between purchased part and supplies. And this indicates the transactions going in this direction. It's 14,000 purchased parts access per hour, 8,000 quotations access from 140 purchased part accesses, and then if you look at this, there are 7,500 accesses coming into supplier coming in this direction, and of those 4,000 transactions are accessing the supplies entity, and then of those 4,000 transactions are accessing the purchase part entity. So you'll see that that number is the same. So as we covered the normalization process pretty extensively last chapter, there may be cases where we need to denormalize it and start putting tables back together, and we'll see how some of that works. But you've got to be very careful about how that process takes place. Now, those of you that have been dealing with computer science or some level of programming for a little while understand how variables are created, and know that once a data is created in memory with a specific data type, it's typically going to stay that data type through the duration of the program. Now, that's not always the case. C++ and some other programming languages have the ability to typecast those variable locations into a different data type, but this is not going to be the case. So in our database design, as we allocate certain attributes to a specific database, a certain data type is going to remain that data type for the life of that database system. So we'll look at how some of that works. So these are just some of the data types that are going to be available to us in that database system. So it's important to be familiar with the different data types and how much memory or how much space each of those data types consumes, because if you use a data type that is actually too large for what's needed, then you're gonna suck up a bunch of a lot of resources that system could use elsewhere, and that's going to be very, very critical when you get into really large database systems or any other systems that utilize those available server resources. So take a look at that. This is table 5-1 on page 211 of your text. So take a look at that and be familiar with that, and how those variables, or in this case the attributes, are allocated. So this is table 5-2 on page 212 of your text, and this talks about some steps that might be used to save space, but there might be other costs involved. So in this table, if you might recall from a few other chapters, we had a table where we had the types of furniture, and then the actual product finish was contained in the table. So what's done here is that the product finish was put into another table, and then via a join or some other relation, the product finish was actually used over here on the product table, and to save space on this area, and then the product finish was only entered once in the new product finish table. So that does indeed save space. The problem there is that when the database system needs to look all this stuff up, it requires a little more processing power and time to take those values under the finished product attribute in the product table and look those up in the code product finish lookup table. So it becomes a pretty critical talent to learn how to weigh those different options and what has the heavier cost on that. And also on page 212 of your text, it talks about some of the abilities to control the data integrity going into the different attributes, and you can certainly do all that in your code as you're writing your SQL, and it goes into some detail about that. But basically, you need to control. Once you specify a specific data type, you need to control the types of data that go in there. So in other words, if you have a data type that set up as date, and I think I might have used this this comparison once before. If you have a data type that's set up as date, and then you try to enter the value of Memphis, Tennessee into that date variable area, that it's expecting a data type, then that's not going to work. So it's important to control the right types of data that go into those attribute areas. And once again, we're getting into the denormalization. So after all the time and effort that we put into our relations in the previous chapter to make sure that they were at third normal form, it might be necessary to kind of back those up a little bit and start jamming the relations back together again. So there are certain benefits of denormalization that can improve performance and reduce the lookup time that is required to access certain variables, and then there are certain costs involved as well. And then now we're going to get into some denormalization opportunities in terms of a one-to-one relationship or a many-to-many relationship, and then the reference data that is used in a one-to-many relationship. So let's take a look at that and see how some of these work. So again, this is, as you'll see in the relation, this is a one-to-one relationship between student and application. And so student has a student ID primary key, and then a campus address as an additional attribute, and then application has application ID as a primary key, and then student ID is the foreign key coming from the student relation. So what was done is that it dropped the application ID entirely, and of course you don't need the foreign key anymore. So we have student ID with the campus address from the original student relation, and then we tackle on the attributes of application date and qualifications to make one new relation that has those two combined. And again, that's for a one-to-one relationship. So now this is a many-to-many, and now you'll notice that there's already an associative entity in this figure, because vendor to item was many-to-many, and this shows the relations as they are currently configured on this the top portion of this figure. Vendor ID and item ID are both the composite primary key for price quote, and price is the remaining attribute in that associative entity. But now look what happens. So in the denormalized relations, we took these three relations, and we have vendor ID as the primary key for vendor, so that doesn't change. So we've taken the price quote and an item and created a new relation called item quote, and again it has the vendor ID and item ID as the composite primary key, and then it has description and price. So again, that takes those three entities and put those back together with the anticipation of some improved performance. And finally, on the reference data denormalization, we have two entities that have a one-to-many relationship, that and the INSTR ID is the primary key for storage, which is the foreign key under item. So we can take both of those together and combine one new relation that has the item ID and description, and the where, store, and container type. And of course that's going to create some data duplication when we put that table together. That's going to probably take a little bit more work in terms of maintenance, but the anticipation here is that the information in these two locations is not likely going to change, or not change very much. So that's kind of why they stuck those two tables together. And if you look at page 217, this talks about partitioning, and this is different from the partitioning or type of partitioning that you might be familiar with in terms of a hard disk or something like that. This is actually partitioning of relations within our database, and this is typically going to be done on very large relations that have many rows and many columns as well. So there is a horizontal partitioning and a vertical partitioning, and we'll take a look at that here in just a sec. But basically, the horizontal partitioning is a separation of rows, and that partitioning can be based on the different types of information that's going to be contained in that one relation, and separate those into more finite groups. And it could be for different user needs, as the slide indicates, and there's more information in the text of how that partitioning works. And then, of course, vertical partitioning is the separation of by column. So you separate that data, and of course you want to have specific columns in the various partitions. One important note on this is that as you separate those partitions, you have to have the same primary key in each of those partitions, so the same data can be accessed. And of course, there's also a combination of horizontal and vertical partitioning.